Hi everybody, it's Mr. Francis again. Here's part 2 of our chapter 11 video. If you made it through the end of part 1, this is where we got cut off. Again, dipole-bipole forces. Again, remember what a dipole is. Dipole is formed due to the unequal sharing of the electron pairs in a covalent bond. The electron pairs are closer to the more electronegative atom, which the more electronegative atom is going to have this partial negative charge. The lesser atom is going to have the partial positive. So now what you've got is this attraction between these dipoles. And again, we saw the chart earlier, so you saw how much energy it takes to break that attraction. Again, these are only present in those polar molecules. So you've got to have that unequal sharing of the electron pair. You've got to have, probably in a structure, you've got your lone pair of electrons on the central atom. You may have some double bonds. Here they're comparing 3 molecules, all that have similar molecular weights. All of them, you can see the difference in the boiling points for the molecules. This final column is what they call the bond dipole, or what we said was the dipole moment. It's that measure of charge separation. The larger this number is, the more polar the molecule is. So the greater that dipole force is going to be for the molecules. And again, this is table 11.2. And again, remember what we looked at with the value of delta H. The more negative the number, the more traction that you have between the molecules. And when we talk about more attraction, look at the boiling points here. The lower delta H's all corresponded to a negative boiling point for a solution. Here's bromine, which exists as a liquid at room temperature. Compare its delta H and its boiling point with the other liquids or the other substances in this table. And again, you can see the dipole moment and the corresponding boiling points for this. So you kind of get a reference. Again, the more polar the molecule is going to be, the more polar that liquid is going to be, the higher the boiling point is going to be for that molecule, for that substance. And that's what we're seeing in this table itself. Hydrogen bonding, again, was very specific. It does, like I said, it is a form of dipole-dipole interaction, but the key in hydrogen bonding are these 3 atoms. Hydrogen has to be bonded to nitrogen, oxygen, or fluorine, or else this type of intermolecular force does not exist, and you're not going to see it in a molecule. And what they're showing you here is, okay, here's nitrogen and hydrogen bonded together, and here's the attraction. So what it is, in the attraction with hydrogen bonding, it's an attraction of this hydrogen atom and the lone pair of electrons on the other atom. So that's why we see that, and that's what we get. Again, these tend to be around the same strength. You can go back to the table that had the strengths of intermolecular forces. It goes around the same strength as or a little less than the dipole-dipole forces, but you add this in with dipole forces, now you've got a much stronger molecule, and it's likely to stay in the liquid state. Water exhibits hydrogen bonding along with dipole forces. And what's really interesting, and I like this part here, the phenomena, the fact that water forms ice, well, we know that, but that ice floats. Water as a solid has a density less than water as a liquid. It's one of the few substances that do that. What happens with the hydrogen bonding is it forces those water molecules to arrange themselves to get that ordered pattern. And in doing so, you get these microscopic holes in ice, very microscopic, but it's enough to lower the density and allow ice to float in a liquid. We'll talk about capillary action and surface tension later in this chapter, but again, hydrogen bonding is going to play a role in those factors also. So again, hydrogen bonding, you see the definition here. The high electronegativity, that's going to be your fluorine, your oxygen, your nitrogen. The lone pairs on those same 3 atoms. So again, you can go back a couple slides and see that attraction with between the hydrogen that's bonded to, say, a nitrogen and a lone pair on a second nitrogen atom. And again, there's our three atoms that form. No other atoms, if they're bonded to a hydrogen, you're going to see this exhibition of hydrogen bonding. So it's very specific in what we have. And again, this 4 to 25 kilojoules, what that is the energy needed to break apart that hydrogen bonding in a substance. Now, here's something really interesting. I mentioned this earlier. Water has that very high boiling point, 100 degrees. So it's actually going to be up here. But look at the other three molecules in that same group: hydrogen sulfide, selenium hydride, tellurium hydride. This is a trend that you actually see within the groups. You see boiling points increasing as you go down the group. Water's an outlier, and it's an outlier because of the dipole-dipole forces plus the hydrogen bonding. And you see the same thing with hydrogen fluoride. And again, follow this trend, HCl, HBr, HI. That's a trend what we see. But because hydrogen fluoride has that extra intermolecular force, it's an outlier in terms of its boiling point. And that's a big thing that we see with molecules and with substances. And again, it's hydrogen bonding. Everything is hydrogen bonding with, as we put this together. I mentioned ice floating. Ice floats because, again, it's less dense than water. They made a whole movie about ice floating. They called it Titanic. The movie sucked. Trust me, it did. But again, it has to do with the arrangement of the molecules. And when water goes from the liquid to the solid state, those molecules actually spread out. That's why when you fill up ice trays, your ice cubes are always larger than the amount of water that you put in there, even though it's the same mass for that. When I talked about that arrangement, the microscopic holes, here's those holes that I'm talking about that get formed because of this hydrogen bonding. That's a big thing. What you're seeing over in the table here is density versus temperature. And as you can see for ice, as temperature increases, you see that decrease in its density. And then once it gets to the liquid state, hey, we've got another increase for that. Again, water is one of the very few substances where its solid is less dense than the liquid. Hydrogen bonding also plays a role in DNA. Okay, very simply, if you know DNA, you know the three components: the sugar, the phosphate linkage, and you know these bases. And with DNA, the bases are always the same that are linked together. Guanine is always linked with cytosine. Adenine is always linked with thymine. But what I want to point out here is where you see these white dashes. There's the hydrogen bonding that is holding together the bases, and that's holding together the double helix linkage that we found here. And that's actually one of the major things in a DNA structure for this. And that's something that's very important. And again, here's another picture. We've mentioned these. This is those electrostatic potential maps. Again, with the colors, the red, the high electron density, the blue is the low electron density. So again, what you're seeing here with the dots, here's your hydrogen, here's a nitrogen, hydrogen, oxygen. So again, there's that hydrogen bonding that's existing in the molecule itself. What we call an induced dipole is one that has been forced, okay? So, and I like the statement here, water can create or induce a dipole in a molecule. So water, if it's close enough to another molecule, they can force that shift in the electrons to form the dipole for a molecule. Here's an example. This is an oxygen molecule, O2. Here's water. As water gets closer to the oxygen, to the oxygen, look down here. You see there's that partial charges. So this attraction that occurs, the dipole, it's inducing the dipole, and it's forcing these partial charges. It's forcing that pair of electrons to get closer to one atom than to the other. Same thing here. Here's ethanol. Ethanol is a very polar molecule. Iodine, I2, nonpolar. But again, normally those two wouldn't mix, but what's going to happen is the ethanol will actually force the iodine for that electron pair to shift. And again, you're going to see the dissolving of the iodine in ethanol itself. Why is the inducement important? Gases. To dissolve gases in a liquid, we have to take into account that many of the gases are nonpolar. That's where the inducement comes into play. And that's how you're able to get oxygen dissolved in water to sustain life there. And again, here's just another example. We saw this slide a couple slides ago. Here's water. Here's an oxygen molecule. As they come close together, it forces that shift in the electron cloud, in the pair of electrons, and you get the partial charges for this. And again, here's some solubilities. Gases, you look at the numbers here. I know these look very small, but again, look at our units. The grams of gas and 100 grams of water, and then it starts to make sense with that. Size matters. So again, when we're talking about polarizability, the ability to shift that pair of electrons to have that unequal sharing, the larger molecule that it is, the easier it is to get that shift in the electrons. And we see that. And as they become more loosely held, they become more soluble. And that's going to be a key. And again, you're seeing a couple of examples here. Iodine molecules inducing the dipoles on themselves, what they call an induced dipole. And that happens. Electrons shift over the course of a period. And you've got to know that shift is going to happen. And every once in a while, for a small instant, you're going to get that unequal sharing that happens. That induced dipole is also what we call London forces, or London dispersion forces. Now, they make a comment here. These are present in all molecules. One of the things I will tell you, you're going to see London forces basically in nonpolar molecules. So that's going to be kind of important for this. But it's also probably one of the weakest of the intermolecular forces. So you're going to see this in molecules that have high molecular masses, ones that have more electrons with it, because again, in London forces, in that inducement, you're getting that shift of electrons. And the more electrons shift, the dipoles are going to form. That polarizability, that ability to shift the electrons, that's what comes into play with London dispersion forces. And again, here's that point. The larger the molecules, the greater we get this polarizability, the greater we get this movement of electrons in here. So polarizability, again, how easy can we get that distribution of the charge changed? How much can we distort it? So can we take a molecule that has an equal sharing of electron pairs and shift it to one of the atoms? The easier we can do it, polarizability. I like that term, squishiness. How squishy is a molecule? It's a decent term. Okay. Now, keep those intermolecular forces in mind. Now let's apply them to physical properties. Boiling point. We'll get into what the definition of boiling point here is in a minute. But again, intermolecular forces, the stronger the intermolecular forces they're going to have a major impact on the boiling point of a liquid. A lot of times, the stronger the intermolecular force, the higher the boiling point is for a liquid. So as you look at this, and all these temperatures are in Kelvin, and you can see, again, the higher the boiling point, the stronger the intermolecular forces. Here's helium, boiling point of 4.6 Kelvin, extremely weak intermolecular forces. Here's iodine, I2, 457.6 Kelvin, strong intermolecular forces, a very high boiling point that we see with it. So one of the things that we can see, the shape of molecules, that branching that comes into play with it. And again, with the intermolecular forces, what we're seeing here is just kind of the amount of energy for, energy and intermolecular forces. And again, intermolecular forces are not strong. Again, compare them to the strength of liquids. So again, here's table 11.5. I like this table because it gives you, again, examples of the intermolecular forces and where we're going to see it. This is actually a really great chart because this will tell you, okay, here's the molecules that are going to, what are we looking for intermolecular forces and where are we going to see it? And there that is. And you compare these two with the molecules and what they see for their intermolecular forces with that. And look at the difference. When you add in a second intermolecular force, here's two molecules, substances, same molecular mass, but an added intermolecular force, much higher boiling point. So with liquids, here's what we're going to see for properties, and all these come into play. I'm going to try to get through a couple of these towards the end of this video, and then in video number 3, we'll get through the rest of them. Liquids are not that easy. Again, what we see for them, ideal conditions, all that with it. And again, it comes down to here, the interaction. What are we seeing with the interaction for liquids? They're in constant motion. The particles, they're in close contact. Again, because they're in close contact, that's why you see the fact that they can occupy any container, but they're limited to the volume. Intermolecular forces play a huge role because we've got to overcome them. Each of those properties that we're going to talk about, we're going to deal with what it takes to break apart a liquid of its intermolecular forces and where that energy comes into play. It's huge. Vapor pressure. The first of the properties that we see here. And again, you look at the definition. The pressure exerted by a vapor over a liquid in a closed container. Always measured at equilibrium. I've mentioned equilibrium in class before. Equilibrium is a lot like a seesaw, a teeter-totter. When you're at equal, you're straight across from each other. When a liquid's at equilibrium, evaporation and condensation occur at the same rate. Not necessarily the same number of molecules, they occur at the same rate. And we can measure that pressure that exists. Get a glass of water, have it with you. Right at the surface of that liquid, there's vapor. It's not very much, but it is. You see it a lot more when water reaches its boiling point. It's when you start to see the vapor come off. And again, they exert that pressure with that. We can tie in intermolecular forces to the vapor pressures. The stronger the intermolecular forces are, the liquid's going to have a low vapor pressure. It's going to have a high boiling point. It's a great tie-in. Weak intermolecular forces is going to be the reverse. It's going to have a high vapor pressure, but it's going to have a very low boiling point. Now, I will add one thing to both of these. When they say low vapor pressure, high vapor pressure, this is at room temperature. So a high vapor, strong intermolecular force, that liquid's going to have a low vapor pressure at room temperature. A weak one is going to have a high vapor pressure at room temperature. So it is an important aspect. And again, you've got some comparisons here, boiling points, the intermolecular forces, comparison with those for that. Okay, I'm going to end this video here. I'm going to pick it up from here on video 3.